Who are you?
My name is Kian, 6129.
Oh, Kian, you came. Okay. Let's go.
The movie that I introduced, my group introduced today is 2012. This movie shows about several disasters in 1 year. So the scene that I want to introduce is the scene that has the highest sea level is 8,000 meters. Like it's impossible because the highest sea level in history is just around 200 meters. And if on ice is melted, the global sea level just rise about 7 meters. So it's impossible. We don't have enough water to raise the sea level to that high. So let's calculate how much water we need to have. So the surface is equal to 4 pi r squared, so we can calculate the surface of Earth is 4 pi 1 multiplied 10 to the power 14, and the ocean accounts for 71% and the land accounts for 29%, so we can calculate the surface of these two. Actually, when we need to fill the water, we have two cases: the case in the left picture and the case in the right picture. Within the same height, the water we need to fill in the right picture will be less than the first picture. So for the oceans, we can calculate the V equals to A multiplied by H and get the volume of the additional over oceans, and we can get for the land we can calculate and use this 7.16 to calculate for the volume of the additional water over land, and for the total additional volume required, we sum these two volumes and get 3954.96 multiplied 10 to the power 6. So to compare with the Earth volume is 1386 multiplied 10 to the power 6, we get the ratio as 2.85. So the conclusion is we will need more than 2.85 times the Earth volume to raise the sea level to this high. And to conclude again, it's impossible for this high of sea level. So to calculate the total wave energy, like I know that last week one group did this topic before and they used the different formula. They calculated using kinetic energy and potential energy, but I found one formula which is simpler than last group. I collect from the physics forum is this formula is equal to 1 over 2 BGHAV squared. And by putting this number into it, we can get the energy as 3.08 multiplied 10 to the power 22. But one of the largest tsunami in history is in Indian is 2.1 multiplied 10 to the power 10. We can compare the ratio is 1.5 trillion times. Like it's impossible to generate this kind of energy. So I have this like.
A and W. What is A and W?
Sorry, A is the energy.
No. Go back. A.
This one.
No, the next. Sorry. L and W.
A and W. The W is 2,000 meters. I haven't written here.
What is that?
That's the width of the wavefront.
What do you mean width?
Like the L is the length, and it's around 1 million meters, and the width is.
Okay. No. I don't need number. Please explain L and W. Definition of L and W.
The W is the wavefront, like it's the width of the wave, and the L is the length.
What do you mean length? Waves continue one after another, right?
It's the lambda.
Okay. Then W, how do you get this number?
Like for the giant tsunami, it will have this value. I get it from the some in the Google.
But how do you know this is the same? How do you measure W? Okay. Please report how do you measure W. Okay.
Okay.
Also, can you consider high tide and low tide? Because high tide, you don't need everything. All the ocean on the earth is not the same height, right?
Oh yeah.
High tide and low tide, right?
Yeah.
So if high tide is at 8,000, then you don't need this much volume of water, right?
Yeah.
Okay. So the time is up. So please calculate this in the homework.
Okay. So this is the normal case. And this is the case, the sea level rise to 8,000 meters. So these all references for these scenes, and this is the end of my scene.
Well, that figure is wrong, right? Please correct that figure. Because
Yeah.
American continent is not as high as 8,000, right? Can you go back?
Which one?
Go back one slide.
This one.
Not this one.
This one.
Like this one. Why we can see not America?
I just pick up.
America is more than 800,000.
I just pick up my random picture.
That is wrong. Please show the correct figure in the report.
Okay. Okay.
Next person, please.
Hi. My name is Pierce. So
Okay, Pierce, please
yeah.
start.
Okay.
Delia, please stop at 4. Okay. We need to switch to the next person at 4.
Okay. And in this movie scene, we see a car drove up a ramp-like stone, and upon leaving, it performed a projectile motion. And the passenger in the car remained intact after the car landed on the ground. And before explaining where the mistake lies, we first make the following assumptions on the ramp angle, initial speed, gravity, ramp height, and the height, mass, and length of the car.
So what's the problem again?
The car leaving the ramp-like stone, and it performed a projectile motion. And I will explain what the mistake lies in later slides. Okay, so first I calculate the maximum additional height reached. At the maximum height, the vertical velocity v sub y will equal to 0, and after rearranging the equation, we can obtain that the maximum additional height equals to v sub y naught squared over 2g, and that would be 1.10 meters. And
Did you write this by yourself?
Oh yeah. I use LaTeX. Yeah, I write by myself.
Good.
Yeah, I use LaTeX, and 1.10 meters plus the ramp height will give us 8.08 meters, and that is the total maximum height the car reached. And in the movie, the total maximum height is only 4.98 meters. So this is the first mistake in the movie. And
Why is the mistake?
because the actual height was 8.08 meters, but in the movie it was only 4.98 meters. In the additional height, in the total height reached.
In the movie it was 8 meters or 4 meters?
4.98 meters in the movie, but it actually should. Yeah, actually it's 8.08 meters.
Then it's fine, right? Within maximum.
The car performed a projectile motion, and when it reached the highest height, it should be 8.08 meters. But in the movie, it only reached 4.98 meters.
I don't understand. I mean, it depends on the angle of the ramp, right?
Oh yeah, I have made the assumption. The ramp angle was 30 degrees, and the initial speed was 20 meters per second.
Okay.
Yeah, so.
Okay, how do you get this 4.98?
Using, it was like twice the height of the car. So we get the specification of this car. This is 2003 Lincoln Town Car Limousine. So it was like, it reaches the 2 times the height of this car. So I get the 4.98 meters.
So you measure it by yourself, right?
Yeah, by myself.
Oh, that's good, but how do you think they shoot this movie, this scene?
Sorry?
How did they shoot such a movie that to make car lower than actual?
Oh, it was made by the spatial effect. I think actually the car, the main character didn't really drive up the ramp-like stone and perform a projectile motion because they will get hurt. So I think that was only made by the spatial effect.
I don't think so. There's some stunt person drove a car, right? Can you show the scene again, please?
Oh, okay.
See, this is a real scene, right?
Yeah, this is the skin in the movie.
Then that's fine. I mean, they shoot it under the physical condition. That cannot be wrong.
But the initial speed would be 20 meters per second, and the ramp angle was 30 degrees. So if we use these values to calculate the maximum total height reached, it should be 8.08 meters. Because that initial speed was really high.
This is the scene that they drove an actual real car to shoot. So they shoot the car should follow the physical law.
Yeah. It should follow the physical law, but if we follow the physical laws.
Something is wrong in your calculation.
On which part?
I don't know, you figure it out. Did you get the weight, velocity, height?
Yeah, weight. The weight was 2,000 kilogram.
How do you know?
I checked out the specification of this car. This car is 2003 Lincoln.
Do you know how many people are inside? What's in the trunk? How many times?
But to calculate the projectile motion, we don't have to consider the mass actually, because there is no any mass involved in these equations.
Oh, right.
Yeah, so
velocity then.
yeah,
What could be wrong? Can you consider what could be wrong?
Wrong is the maximum total height reached. It should be 8.08 meters.
No. In your calculation, okay. Do you understand what I'm saying? Your calculation is wrong because this is a real scene.
Oh yeah.
This is not computer graphics, right?
Yes.
This is not a cartoon. This is a real scene. So real scene follow the physics. So your calculation is wrong. Do you understand?
Which parts?
I want you to consider which part, okay? Okay. Yes.
Yeah.
This is wrong. So you need to correct it. You need to correct your calculation.
Oh, okay.
In your report. Okay, 4.98 meter. I mean, this means okay. Your calculation is wrong.
Oh, okay.
Find out what's wrong.
Okay. So.
Okay, next person, please.
I'm Peggy, and I'm going to introduce the third scene.
There's no such student.
Excuse me?
Are you Jenny or are you Peggy?
Oh, I'm Peggy. I'm Peggy. Peggy.
Okay, please remember your name.
Okay. In this scene, we can see that the car crashed into the building's glass with the...
Can you play that again?
Huh? What? Oh, okay.
Play the scene again.
This scene is right after the scene he introduced. and we can see that the car braked through the building's glass, and the glass broke, and the car continuing forward without significant harm to the car and the passengers. And I have two questions about this scene. Is that whether the car can realistically break the glass, and would the passenger inside truly remains unharmed after experiencing such a forceful collision? To calculate these are my assumption, and some of the data is same as the assumption he makes. Yeah. And then first I calculate the first question: can the car break the glasses? And first I use the impact force, which is the mass of the car times the velocity of it, and divide the contact time. And these numbers it's just like I assumed before. Yeah. And I got the data of the force of 400,000 newtons. And then I can calculate the stress on the glass.
Okay. Peggy.
Yeah.
I have the same comment. But this scene is really taken with a real glass and car, right?
But we can't make sure of that. Maybe they use some bumps, or I don't know how they sing this part.
Can you show the movie again? So you think the car should be stopped by the glass? Is that what you think?
I'm not sure, because I have another calculation on the other slice. Yeah,
What's the conclusion of the first slide?
First view of this thing is from the local stress, and it is insufficient to break the tempered glass. But they also have kinetic energy. What?
Go back.
Go back. Yeah.
What's the conclusion here?
The local stress from the car isn't sufficient to break the tempered glass.
So how did you get A? What's A?
A is the I searched on the internet, because the car have this one, the front bumper, and this is the part that will contact the glass for the first second. So
Okay, go to next.
yeah. So using this A and the impact force I calculate previous, so we get the impact stress on the glass might be 4 million pa.
Oh, okay, Peggy, you're saying there's a glass wall,
What?
and then mean time hits the glass wall, and then you're saying glass is not going to break.
Yeah, in the view of the stress, that might not, but the result might be different in the past slice.
Is that true?
Actually, I view from two part. First one is the stress, and then is the energy. So if view from the energy, the glass might broke. And this is the part I calculate that from the energy view.
How did you get this 300 megapascal?
What?
300 megapascal, how did you get it?
I searched from the net, because they say in common sense we use the fractional energy density of glass about 10 to the 6 joule per meter cubic.
That's very big number.
Oh, really? Because I saw that in the information on the net.
what's the velocity of the car you are sure?
What?
The velocity of the Lincoln.
Oh, I use 20 meter per second.
Okay. I think this is wrong.
Oh,
Lincoln can break the glass usually,
what?
even tempered glass. Can you, in your report, can you check these numbers if your computer is correct or not?
Oh, okay.
Can you go back? Maybe the area is too large.
The area? You mean this one?
Yeah.
It's too large or what? I didn't listen clearly.
So it's wrong.
Oh, it's wrong? Okay.
Delta T, how do you know 0.1 second?
Oh, but this is my assumption because I think the
I'm asking where did you take this assumption?
I just watched it in a movie and I used the time clock. Is that?
That's a problem. Take more realistic number and recalculate, okay?
Oh, okay.
But I mean, common sense, come on, I mean, Lincoln hit the glass. Glass is going to, of course, break.
Yeah. So I have the conclusion here that the energy can.
Energy, the previous one.
Oh,
right?
this one.
In terms of pressure, you said the glass is going to be break, right?
Yeah.
So this slide is wrong, okay? So please correct in your report.
Okay. So, do I have to move on?
Yes, next person.
Hi, I'm Jenny. And I'm going.
Jenny.
This is my scene. So, in reality, the RV is unlikely to reach the speed because of the incline and force acting against the RV. So first, I'll calculate the size of the RV. The length is normally 6 to 10 meters and weighs between 4,000 and 6.
What is the problem? What is the problem?
Oh, so the RV is unlikely, so it cannot reach the speed to fly over the crack. Here, so it cannot like fly over the crack. And so first yes?
You're saying the speed of the RV is too fast?
Yeah, like in reality, because there will be like forces and like resistance, so it will not be able to reach the speed.
Okay.
So I assume that the RV is 8 meters and 6,000 kilogram. And the crack is like, from the picture, you will see it's about 1.5 times of the RV, which will be 8 times 1.5 is 12 meters. And then I estimate the slope. So the rise is 3 meters and the run is 12 meters, which is the crack. And I will get the degree of 14.04. And after, I'll calculate the speed that you need to fly through the crack. So I'll use this formula, which is the speed equals square root this formula, and then I put the numbers inside. So the acceleration due to gravity and the meter. So yes.
What about height? Height. I mean, the other side of the crack was lower than this. The other side, right?
The other side of it's about like this.
no. Straight again. So when they show the height.
The height of the crack?
Movie. Show it again. Yeah, stop.
What do you mean again? The height?
Did you notice that the origin, both sides of the crack?
Yeah, so so there's a slope, and that slope is like 14 degrees.
I'm not talking about slope height.
Height?
Yes, height is different. The RV is just falling down.
Oh, I didn't include it in my calculation. I'll put it in the report.
Okay. So what's your conclusion?
So to reach like the speed have to be 15.81 meters per second. But because like there is
So how many kilometers per hour? That speed, how many kilometers per hour?
56.92.
56? That's RV can do, right? They can be on highway.
Yeah, but yes, so I will explain. So that RV can reach a speed of 120 and 140 kilometers per hour. But because there will be like vibration and the floor is like uneven, it's uneven ground. So there will be like forces to make the speed slower. So there will be like effect on the gravity. So here I'll calculate the gravitational force that act against the vehicle. And the gravitational force is 14,260 newtons. And next, there's also resistance of the going through the slope. And the resistance is 2,850 newtons. And after I assume that the RV have a total force of 20,000 newtons, and you have to use 20,000 to minus like the resistance force, which is 14,260 plus 2,850, and I'll get a number that is 2,890 newtons. And using Newton's second law, so I'll get the acceleration, which is 0.48 meters per second. And after I calculate the speed again, and I get, so because of the resistance, the RV speed can only reach like 6.93 meters per second, which is 25 kilometers per hour.
This is good. So please calculate.
Yes.
What's the best angle for RV to jump from this?
Jump through the crack. Okay.
So this is saying top grade is too steep for RV. So what's the best angle for RV? Okay.
Excuse. Can you say it again? I didn't listen carefully.
Please calculate the optimal angle the RV can jump most.
Oh, okay. And so so next person.
Hi, I'm Conrad. My student ID is 1100100002.
Hi, Conrad.
Hi. Okay, so I'll play the clip. Oh. Okay, so here's the timeline of the actions in the movie, and then I turned it into a graph here. So the plane starts to accelerate for 27 seconds, and then at the 18th second, Jackson was the main character running there, and then he starts running under the constant velocity, and then from the 27th second to the 45th second, the plane stops accelerating. And then for the calculations, I assume that they start at the same line. So it will be easier for Jackson to catch the plane. Okay, so scenario 1, I didn't consider the friction here. The friction will be considered in scenario 2. So I assume the acceleration of the plane will be 3.2 meters per square seconds, and then it will travel under constant speed during the 27th seconds to 45th second. And then first we calculate the distance traveled by the plane. So it will be the distance traveled during acceleration, and then plus the distance traveled during constant velocity. So here's the distance traveled under constant velocity, and here's the distance traveled under acceleration. So then we add them up, and then for Jackson to catch the plane, he needs to run the same distance as the plane. So here we get the he ran for 27 seconds, so the distance divided by the seconds, then we get how fast he should run to catch the plane. So after calculation, he needs to run 100 meters per second to catch the plane in the scene. Okay, for scenario 2, I considered I considered the friction between the runway and the tires. So for rolling tires, the effective coefficient of friction is 0.02. So there should be a acceleration backwards by the friction to the plane. So this is the acceleration backwards on the plane. Okay. So I did the same thing, and then I calculated the distance traveled by the plane during the 27th seconds to 45th second, and then also the acceleration period, the distance traveled by the plane. Okay, so I add them up, and then also it's the same thing. So for Jackson to catch the plane, he has to travel the same distance as the plane. So I do so I divide the distance by the plane to divide it by 27 seconds, and then we can know that he needs to run 93.3 meters per second, which is faster than the high-speed rail in Taiwan. And then also the fastest animal on Earth, the top speed of the peregrine falcon is actually 320 kilometers per hour. Okay, so this is the real life scenario. So I was trying to calculate the if it was Usain Bolt who was chasing the plane, how long will it take to catch the plane? So so now we don't know the time, but we have the velocity of Usain Bolt. So I got the distance, which is a function of t here, and then so I just this formula, and then I try to get the t here. So after calculating, I got the t, which is 746.5 seconds. So which means he needs to run from the 18th seconds to this point. So he needs to run like 76 100-meter races in top speed. Okay, so the conclusion is Jackson Curtis, which is the main character, cannot catch the flight. He even if he catches the flight, he needs to run 10 times faster than Usain Bolt. Okay, and this is the video that follows the correct physics laws. Okay, so and the video is done by me and Jenny, and there will be sound effects, but we can't play it here. Yeah, that's all.
I have the sound effect.
Oh, really?
This
Okay.
This is very excellent. Very nice.
Yeah, okay. So I'll give it to the next person. Or are there any questions?
Yes, very good job, comrade.
Yeah, okay, thank you.
Very good. Who's next? My class time is up, but let's finish. Who's next?
My name is Ryan,
Okay, Ryan, let's go.
and there's a scene that shows a small plane flying through a volcano eruption, separating from the fire and ash, which is not possible in real life. What's wrong in the scene is that the engine will melting and resolidify inside the engine because there's the heat is too high, will melts the engine, and that's a calculation. And that's the ash which will intake into the engine by my calculation. So with that much of ash intake into the engine, so it will cause the engine will be failure to work. So the airplane will be fire and crash.
How much ash can an airplane take?
Sorry, can you say it one more time?
How much ash can an airplane take?
I don't know. I didn't put it in my calculation.
Then how do you know it's going to break?
Because the airplane cannot afford that much of heat.
Okay. How
Yes.
much heat? Sorry. So what about the ash? So there's no conclusion from the ash?
Sorry, can you say one more time?
So the temperature difference, how do you know?
I assume the temperature.
How do you know it's correct?
I do some search on net, but yes, I assume the temperature.
Okay. So that's not good enough.
Oh,
So
okay.
please, in your report, clearly specify where do you get this temperature, okay?
Okay, okay.
And the mass of the ash, how do you calculate?
I
Mass of
didn't.
the ash, How you calculate?
I didn't do the total mass of the ash. It just the number is just for 1 gram of ash. The number is for.
I don't understand your presentation. Okay, you need to better explain. Here, M, mass of the volcanic ash, and you are saying it's 1 gram.
It's the number is each gram of volcanic ash will produce.
Okay.
Yes.
Then, okay, how do you know that the airplane cannot take this heat? How much mass of ash the airplane took?
Oh, here.
Okay. So this is the amount of the ash, right?
Yes.
And then total heat is calculated where?
I didn't show it in my presentation.
No? Then how do you know if the heat is too much?
I don't know.
This presentation, I don't think it's complete.
Okay.
You need to show the conclusion with numbers.
Okay.
Okay, this number is greater than this number. That's what we need.
Okay.
Please do this in your report.
Okay. Okay.
Next question, please.
Thank you.
Owen, right?
Yeah. Hi, Professor. I'm Owen. And here I want to talk. Here the scene I want to talk about. So here's our signal problems.
Let's explain by word.
Okay. This scene I found a problem in about the scene is about if you can see they just get on the plane and they just take off in the very short distance and in additional they take off in the very short time also, and I think it's a very violated physics law. Yeah, just like that.
Okay. Please show me.
Okay. Here, first we can get to know about the this model of aircraft, and here's some information.
Okay.
It's a twin engine.
Next slide.
Sorry.
I got it. Next slide, please.
Next slide. Okay. Here I found two formula to calculate the lift force of this aircraft. Is the weight the massive multiplied by the gravity for the and the other one is using the air density at the sea level multiplied by the wing area and the maximum lift coefficient. And here is my calculation to get the accelerate to take off and the fness to do it. But
Okay.
this force is not our final force to let the engine to can live up in the very short distance. And here is continue calculation. We need to add the rolling resistance force into it. And here I calculate it have two parts, is F rolling and the F rod. First, the F rolling and calculate by the rolling resistance coefficient multiplied by the massive and the gravity force. So it's gonna be at 480 Newton. And for the drag, I have a formula for is about a half of the velocity average velocity square multiplied by the swing area and multiplied by the drag coefficient during takeoff. So my final F first is F nest plus the F resistance is gonna be 4,424 at 22. I can see it clearly. Yeah, 22 Newton. And then is a reality is need to in the real life effort of this model of aircraft, because based on my research about this website, yeah, is given about the takeoff distance, yeah, here, yeah, in the real life, and here in this scene we will find what wrong with this. In here we can see that I just visualize the distance, just like it can be put in about 15 to 20 aircraft inside the side object into this distance. So it might have about 200 meter length. Yeah. So they given the takeoff distance is 200 meter. So at above, above calculation, we can recalculate the effort of this thing is about 10,000 Newton. So which is 127% greater than our real life standard takeoff distance. So it might be a very ridiculous things and very hard to happen. And if you find still are so convinced you for this calculate, I addition some more information is about the time to let them take up. Is yeah, it is, we can see that they just take up about a few seconds, just like a 5 second. Yeah, it's make it even more impossible. The needed accelerate and the thrust forward for imagine is imaginable for a small motor aircraft. And here is my just like previous calculations that you can calculate the third total forward and the thrust forward per engine, because it's a twin engine motor aircraft. Okay, and then but you can see that maybe in the movie they just make the.
Oh, I don't understand. First, what's the relation of your number? You calculate 10,000 Newton, right?
So can you see?
Why this is too much? How do you compare this number?
Compare these forward.
Okay, your conclusion. Can you understand your relation between your conclusion and your calculation? You get 10,000 Newton, right? So why did this what's the relation of this to your conclusion?
You mean the acceleration or the? So sorry, I can hear you clearly.
What is your conclusion? And then show me from the number.
Oh, so just like you can see our real life our real life effort to make the aircraft lift up to take off is 4,422 Newton, but but my next two calculation about the scene in the movie, you can see that the number of third fort is required is one is 10,000 and another one is even approximately to
Why
20,000.
so much bigger?
Yeah, too much bigger. And
Why?
we
Can you explain?
sorry.
Why your number is so much larger? Can you explain?
Because it's in it just need a very short distance to take off and the
So, where in your calculation you use this 200 meter?
sorry
Where in your calculation you use this 200 meter?
200 meter. Yeah, here.
Oh. Okay. Then when you calculate how much runway is needed to meet this,
How much for what?
how much runway is needed so that it works?
Can you say it again? I can hear clearly.
How long is the runway needed? Please calculate. Right?
How long did the runway needed to just?
Yes.
It's about 500 meter. In the real life.
No. Show the calculation. How did you calculate it?
So, I don't understand you what you mean. Oh, sorry.
I don't understand your presentation either.
Because my opinion is we compare to.
Okay, so this calculation is probably going in a wrong direction. I don't think it's wrong, but it's not the right direction.
Yeah. I know that. I
Okay.
also think of the
Start from the power of the airplane engine power.
Yeah.
then
I know that.
Calculate me how long runway it needs. Okay, this is your homework.
Oh, okay.
Okay, let's stop here. So that's everyone, right?
Yeah.
We don't need a time for the. We don't have the time for Kahoot. So let's finish here.
Okay.